Hello. Today I'd like to go over what I consider to be the two hardest problems in the Kinematics 2D Kinematics package. First one is this lovely hot air balloon, which is firing a projectile, I guess a ball, at an angle of 42 degrees to the horizontal. And it goes up in the air and ends up on the ground a certain distance away, and we're trying to find this distance. It has fallen a certain vertical height from when it started. So let's talk her over. First of all, we got initial velocity at an angle, and what you will do basically every time you have that is you will find the horizontal and vertical components and then never use your diagonal initial velocity ever again. So your initial velocity in the y direction is going to equal 19 times sine 42. And your initial velocity in the x direction will be equal to 19 times cos 42. So now that we found the horizontal and vertical components, we're going to use our y information to figure out the time in the air. If we're just looking at our y variables, why don't we separate these out and just list what we know, because that is always an amazing idea. Vertically, we know, and I'm going to say that up is positive and down is negative as my convention, and everything else is to the right. So I'll just make everything right positive, and there's nothing left, so I don't need to worry about it. So vertically, my initial velocity is 12.7, and that's positive because it's up. And my initial horizontal velocity is 14.1. My acceleration vertically is going to be negative 9.8. And my horizontal acceleration is 0. No side gravity, nothing funny going on there. We're not dealing with air resistance. Vertically, my displacement, you'd be tempted to put in 25, but keep in mind this ball is ending up 25 meters further down than when you started. So let's make that a negative 25 because the ball has ended up further down than when we started, and we said down was negative. We're looking for displacement horizontally, and that's not a bad place to start. So it'd be really like we want this horizontal range. To do that, we can find that super easy as long as we had time. And time is the one thing that transfers over between vertical and horizontal information. With this information right here, it's pretty hard to go straight for time. But at this point, vertically, it's basically exactly like some questions you probably saw in the Snap book or in a previous test or practice test, or probably both, maybe involving a construction elevator and a physics textbook. Anyway, if you remember your strategy for that one, it's exactly the same. It's hard to go directly for time, but we can go for final velocity. And so that's what we're going to do. We're going to say, hey, my final velocity is equal to squared is equal to vi squared plus 2ad. We've got our initial vertical velocity of 12.7, and we are going to add that to 2 times negative 9.8 times negative 25. Remember, you will get this wrong if you get that negative wrong. And we'll take that square root and find VF. Now, when I put that in my calculator, I got 25.5. But I did have to take a square root when I did it. And anytime I take the square root, just like the square root of 4 can be 2 or negative 2, but your calculator will only ever say 2, I need to decide whether this should be positive or negative. And I said negative was down. Do I think it was moving down right before it hit the ground? Heck yeah. So I'm going to make that negative. So this is a negative we figure out because of logic. So careful with that. Anytime you take a square root, you gotta think her through. Now you know how like acceleration is equal to how much your velocity changes per second. So this kind of definition, rate of change of velocity. We can rearrange this into an incredibly useful formula. Time is how much your velocity has changed divided by the acceleration, how much it's changing every second. So that would be negative 25.5 minus our initial vertical velocity, which is 12.7, and divided by negative 9.8. And when we put that in our calculators, we will get 3.9 seconds. So using our vertical information, we have found that our time is 3.9 seconds. Vertically, it's taken that long to hit the ground, and it's exactly the same horizontally. That is the one thing that can go between. So that is super useful, and we can use that horizontally. So now we'll do a little horizontal formula. Now horizontally, we could just say, hey, displacement is your average velocity or initial velocity times time. Maybe I'll just do this, VIT plus 1/2 AT squared. But what's my acceleration horizontally? There's no side gravity, so this thing is just 0. And my displacement, my range, which I'm looking for, is just equal to that 14.1, I believe. Yeah, 14.1 was the horizontal component of my initial velocity times our time, which is 3.9. And if we do that, we should get about 55 meters. And so that is our range. This is the final answer. So again, recap, 3 major steps. We broke it into horizontal and vertical components and then never use this 19 again. That'll be a common theme. Anytime you got initial velocity and angle, find your components and then ignore it. We laid out all the variables we knew, separating out vertical and horizontal because they have no effect on each other. It's pretty hard. We wanted to use our vertical information to find time, so that could transfer over to horizontally, and we can use that to find our horizontal range. But it's hard to go straight for time, so we found final velocity first, being careful that when we took the square root to make that negative, because it was moving down then, and we're being consistent with what we said our sign convention is. And then we used time is change in velocity over acceleration. It ended up moving down at 25.5 meters per second and started going up at 12.7. So we did our change, divided by negative 9.8, got 3.9 seconds. And then we used that 3.9 seconds in our horizontal formula, where our acceleration was 0, to find our horizontal displacement. That's how it's done. Bit tricky, but more because there's a lot of steps than any step is terrible. Now, last one I'm going to go over in this video is this guy right here. It's honestly not terrible, but the fact it wants both magnitude and direction is a bit of a pain. I'm going to show you the component method of doing this. There is a kind of sine cosine law way, but I'm not going to mention that right now. So first thing, we've got our velocity at an angle. So I'm going to find the horizontal and vertical components. My initial y velocity is going to be 25 sine 35. And my initial x velocity is going to equal 25 cos 35. So just like before, like we found our y initial velocity component and our x initial velocity component, and then we'll ignore this and never use it again. I'd sure like to know the time it was in the air. Now with the last question, we had enough information vertically to figure out the time. But in this one, it's horizontally. Like there's no side gravity. It went 40 meters. It's going about 20 meters every second. So with rounding, it went, let's say, time is equal to displacement, like your total meters divided by your meters per second. So we went 40 meters and we're going about 20 meters per second. So we'll find out it'll take 2 seconds with rounding. So it's 2 seconds in the air. We're using our horizontal information to find that. Now that we've got the horizontal information, our horizontal component's not going to change. So that one's set. All we really have to do is figure out how much our vertical component has changed. And to do that, we'll just say, hey, so this was horizontally. Vertically, our final vertical velocity is equal to our initial velocity plus AT. I'm going to again use the sign convention that up is positive and down is negative. So initially it was moving up at 14.3. Gravity is down at 9.8, and it was acting on it for 2 seconds. So it's going to change its velocity by 19.6 down. So that's going to equal 5.3 meters per second down, or negative 5.3 meters per second. So then we've got our total final velocity, which is the same as our initial velocity horizontally, and we've got our final velocity vertically. Now we can just make a lovely little triangle. So I'm going to draw my horizontal first, which is 20.5, and then draw my vertical tip to tail, which is 5.3. Notice I've dropped the negative now because that information is encoded in the direction of this vector. So if I throw in another negative, it's just confusing. And so we're looking for that. We're looking for this kind of like side, and we're looking for this angle. So x here is equal to 20.5 squared plus 5.3 squared, all square rooted. And then theta is equal to the inverse tan of opposite over adjacent, which in this case would be 5.3 divided by 20.5. Remember, inverse tan takes the side ratio and gives you the angle, which is what we want. So we find out that at the end, right as it's hitting the wall, it is moving at 21.2 meters per second at an angle of 14.5 below the horizontal. So 21.2 meters per second at 14.5 degrees below the horizontal. And that's how it's done. Thanks for listening. Hopefully this was helpful.